How are you?
Good. You?
Good. I'm looking at this second page you sent me, and you can see that it's not very clear. Do you have that in front of you? Can you take another picture of it and send it?
Sure can, Dad. You'll do it right now.
Yeah, go ahead and do it. I can make out enough of it that we can go ahead and get started, but it might make the rest of it easier if we have a little clearer copy of it.
You know, David, he might be able to hit it with a flash. I don't know if we did that or not, so let him try again.
Okay.
Send you a new copy.
All right, let's look at 15. Graph the function showing at least 5 points. Let's look at your two tables here. Looks like you did 6 points. What is y when x is 0?
That would be 4.
Correct. In other words, 4 goes right there. What is y when x is 1?
5.
What'd you say?
5.
Okay, what's the cube root of 1? That is cube root, is it not?
Yes, David, it's y equals -2 cube root x plus 4.
Okay, so when I plug in 1 for x, first of all, what's the cube root of 1?
1.
What's -2 times 1?
-2.
What's -2 plus 4?
2.
So 2 goes right there. Six. You see what the problem is with inserting 6 for x?
Yeah, it's not a cube root.
Well, it's not a perfect cube, which means we would have to give it's not that it doesn't have an answer, it does. It's just not a whole number. And we would have to go to a calculator to get it. So, what's a better number than 6?
We could do 8.
There you go. What's the cube root of 8?
2.
What's -2 times 2?
-4.
And what's -4 plus 4?
0.
Okay, so let's put 8 there and 0 there. Now, they said they only needed 5 points, so let's do 2 more. What is this point right here? That looks like a U.
I think there's 6s there. I think
It's a 4.
4 and a 6.
Okay. Is -2 a good point to use for x?
No.
Okay, how about -1?
No.
Actually, -1 is fine. Why? Because what's the cube root of -1?
Oh, -1.
In other words, as long as it's a whole number, then it works just fine. So now, what's -1 times -2?
2.
And what's 2 plus 4?
6.
So when, cross this one out, because we don't want that one. And when x is -1, y is 6. And we need one more point. Is 4 a good point?
No.
What would be another good point? We've used 0, 1, 8, -1. We need one more.
Could you use -8?
Yeah, let's do it. What's the cube root of -8?
-2.
Correct. -2 times -2
is 4.
4 plus 4.
8.
Good. Sounds like you've been practicing.
He's been sleeping.
Really?
Yeah, he had a good night's sleep last night.
Seriously, because
Plus some of the stuff he really is much more adept at than
yeah,
others.
yeah. Actually, it almost sounds like you've been practicing on A+ math, because your
Yeah,
arithmetic is much quicker and very accurate.
Yep, we ended off strong last night and strong this morning, so we'll see where it goes.
Good. All right. So we got our 5 points. Now, let's talk about transformations. What's the elementary function? We can't really talk about transformations unless we know what the elementary function is.
Would be cube root x.
Very good. And 3 things are going on here. What are they?
A reflection.
Can't just say reflection, you have to say reflection over which axis, because you can have both. You can have a reflection over the x-axis, and you can have a reflection over the y-axis.
So it would be a reflection over the x.
Yeah, if my negative sign is in front of the function, it's that. If the negative sign was like that, that would be a reflection over y. They may not have even given you any of those yet. I haven't seen any yet, but that's also a possible reflection. What's the consequence of the 2?
A horizontal shrink of 2.
No. Remember, it's in front. In other words, let's talk about another way of expressing this. That 2 is in front, which means it's like this. When the 2 is in front of the function, like that, it's a vertical stretch. Okay? There's only 6 things you can do. You can reflect over the x, you can reflect over the y, you can vertically stretch, you can horizontally stretch, you can vertically shift, you can horizontally shift. That's it. Those 6 things. When you're talking vertically stretching or shrinking, it has to do with a number in front of the function. If that number is greater than 1, it's a vertical stretch. If it's between 0 and 1, it's a vertical shrink. So this right here needs to read vertical stretch by 2. I can understand why you said horizontal shrink if that 2 was inside. In other words, let's write this slightly differently. If we were to write f of 2x, that 2 is a horizontal shrink. But then the function would have to look like this. If the function looked like this, that would be a horizontal shrink. But it depends on whether that 2 is inside the function or outside the function. And finally, what's the consequence of the +4?
Vertical shift up before.
What's the domain of this function?
Would be -1 to infinity.
Can it be -8?
Oh, yeah, it'd be -8 to infinity.
Can it be -27?
No.
What's the cube root of -27?
Oh, 3.
-3.
Negative.
In other words, we can take the cube root of any number, positive or negative. It's not like square root. Square roots, we can only take square roots of positive numbers or 0. Cube roots, we can take square roots of negative numbers, we can take cube roots of positive numbers, and they come out with different answers. So the domain is all real numbers, -infinity to +infinity. There is no value for x that doesn't work. What would that make the range?
that make it negative to infinity to positive
Yes,
infinity?
all reals also. In other words, as long as we can make this be any number we want, and we can, positive and negative, then y can be any number we want, positive and negative. All right, let's graph the elementary function first of all. The function I'm most familiar with, this is what I would call the elementary function. Only they've taken the inverse of it. This is what they are calling the elementary function. Well, when you take the inverse of something, it reflects it over the line y equal x. So it ends up looking like that. So that's y equal cube root of x. The negative sign, always start with your reflections. Don't do your vertical and horizontal shifts first, otherwise you'll end up getting a different looking curve. So if we start with the negative sign in front, I'm going to draw these dotted. Basically gives you that. In other words, this is y equals negative cube root of x. Excuse me. Negative 2 merely means it's a vertical stretch. In other words, and the way to think about that is if this was negative cube root of x, well, we're going to be twice as far away from the x-axis, so that point would be there. This point would be here, this point would be there. The net effect would be, let me draw it in blue, something that looks like this. In other words, that's a vertical stretch from the dotted red line. So this would be y equals negative 2 cube root of x. And finally, the last thing that they're doing is shifting it 4 up. So all that means is take this point right here, move it up 4 to there, and you have something that looks like this. I think it's helpful to do each of those transformations separately, just so you can see the effect of all of them. So the curve that they want you to draw in here should look something like that, the solid blue line at the top. All right. Here. Okay. Write the equation of the cube root function with the following transformations. So what's the equation of the elementary cube root function?
3x, 3 to the x to the third root.
It's the way you pronounce this is the third root of x, which is different than x to the third power. These are actually inverse functions of one another. An inverse being something that undoes something else. In other words, if I've taken a number and cubed it, if I want to get back to where I started from, I take the cube root of it. So these are inverse elementary functions, and this is the one they're talking about, the cube root function. So reflecting it over the x, what would that do?
It would put a negative sign
Where?
before the 3.
Vertical stretch of 3, what would that do?
That would put 3 between the negative sign and the square root.
The radical sign, yeah. This thing here is a radical sign. And you can have if there's no number here, it's presumed to be 2, so it would be presumed to be square root. It could be cube root. It could be 4th root. It could be 5th root, whatever. Okay. Horizontal shift to the left of 1.
Would that be -1?
That would be a shift of right to the 1. In other words, if I had -1 like that,
It'd be the opposite, so it'd be +1.
right, that's to the left. And it's inside the function. In other words, this is f of x plus 1, as opposed to f of x plus 1. See the difference?
Yeah.
This is kind of an important distinction on these, although you seem to be pretty good with these, so I don't want to confuse the issue. And vertical shift up of 4.
+4.
Where? Inside the radical?
No, at the outside.
Outside the radical, like that. Okay. Might have to help me with reading some of these.
Oh, I sent another picture.
Okay, here, let me open it up.
I'm just gonna
Yeah, much better. Sometimes it's just a steadier hand. I've taken an awful lot of pictures and digitized math problems into my computer, and boy, sometimes it's just kind of random as to how steady your hands are. All right, let's write this fully. Now, right off the get-go, I can't do anything here. I'm dealing with apples, oranges, pears, and peaches. But if I can simplify some of these radicals, I might be able to turn them into similar things. Can I simplify root 18?
Yeah. You could do 6 and 3.
Problem with 6 and 3 is that they don't turn into whole numbers.
You could do 2 and 9.
There you go. So this is root 9 times root 2. We'll start there. And then we're going to turn that into 3 root 2. Okay? How about root 27? Does that have any factors that are perfect square numbers?
You could do 9 and 3.
Okay, so let's write it like that. Square root of 9 times square root of 3. What's square root of 9 become? And what does this become?
Square root of 9 becomes 3. The square root of 3 becomes the square root of 3. And
Hold on. We're multiplying 2. In other words, we can't multiply this 3 times the square root of 3, but we can multiply 2 times 3.
It becomes 6.
So I can turn that into 6. Let's Still can't do anything with these two things because this is a square root of 2, this is a square root of 3. But now we have more square roots of 3. And square root of 8 becomes what?
Square root of 8 becomes 4 and 2.
Square root of 4, square root of 2. What's this become?
It becomes 12.
Now we have only apples and oranges. We got apples here, we got apples over here, we got oranges here, we got oranges there. Let's combine them, end up with just one set of apples and oranges. So how many root 2's do we have?
2.
We got 3 over here, we got minus 12 over here.
There's two functions, so you didn't you're talking about different things.
Yeah. So we would have minus 9.
Okay. Minus 9 root 2's. How many root 3's do we have?
We have 9.
No, don't drop the signs.
Oh, we have minus 3.
Okay. That's our final answer. We've simplified it as far as we can go. We can no longer combine the root 2's with the root 3's, but we've got it as exact as we can express it.
And Dave, is that x equals, or is it just...
No, this is not a function. This is just an expression.
Okay.
In other words, or I should say numbers. That's a number minus that number. I don't even know what decimal number that would equal. You don't want to make it a decimal number. In other words, the moment I turn that into a decimal, I've made it less accurate. If I want it to be the most accurate depiction of that value that I can possibly make it, you're looking at it. It's minus 9 root 2's minus 3 root 3's. That's a number. All right, here we're multiplying. You know, it doesn't matter if you're talking variables, numbers, complex numbers, radicals. You're going to do ET with all of them. So what do you get?
You get negative 6.
Hold on. Positive 2 times positive 3.
Oh, you get 6.
Uh-huh. It's only the sign in front that matters, not the sign afterwards. Next term?
Would you get square root of 5?
Well, we got to multiply that times that.
So you get 2 square root of 5.
And I'm going to add that. In other words, every time we multiply a term by another term, we're going to add or subtract it. So what's next?
Would you get 3 square root of 5?
Here's where you can't drop that negative sign.
Minus 3.
There you go. And finally, what is minus square root of 5 times plus square root of 5?
Would that just be square root of 5?
Well, if it was square root of 5 times square root of 5, that would be 5. But if one of them is minus, then it's going to be minus 5.
All right.
Okay? In other words, square root of x times square root of x is x, no matter what x is. In fact, the square root of anything, the square root of x plus 1 times the square root of x plus 1 is x plus 1. In our case, we had a negative sign attached with it, so it was minus 5. Now let's combine these 4 things. How many numbers, how many real numbers well, not real numbers, excuse me. How many rational numbers do we have?
You have 1.
and it's 1. 6 minus 5, right? Gets rid of that, gets rid of that. How many root 5s do we have?
We have 5.
We have 2 minus 3.
Oh, so you have negative 1.
Right. Negative 1 root 5, which I can write like that. Again, that's the most accurate depiction of that value. Okay. Here we're multiplying, but we're only multiplying one term times two terms. So it's just a straight distribution. What's this term going to be?
Wouldn't that be square root 2 to the 3 2 to the third?
You're making it harder than it is. The thing you need to know is if I have the square root of a times the square root of b, that's equal to the square root of ab. So multiply the square root of 5 times the square root of 3, what does that leave you?
Would that be the square root of 15?
Correct. And then I still have this too. I can't ignore it. So that's what those combine to be. 2 root 15. Now what's square root of 5 times square root of 5?
That'd be 1.
5. It's whatever is inside the radical.
Okay. Yeah, sorry.
That's right. So there's your answer for that. And I can't reduce that. In other words, I can change square root of 15 to be square root of 5 times square root of 3, but that's not considered simplified. In other words, now I have two terms instead of one, and both terms are radicals. In other words, I didn't pull a number out. If you can't pull a number out, you don't want to do this. You want to leave it as one term, root 15.
Page 17. Newton.
All right, this is going to be a trig problem. Whenever they give you a ladder problem, know that it's all about sides and angles. So I'm going to draw the picture. There's the ladder. Help me label this diagram. What's the length of the hypotenuse?
Yeah, 12 feet.
What's the length of the bottom of the ladder from the wall? In other words, the x.
5.
So they want to know y. Right?
Yeah.
Well, we always know that anything that's like a ladder or a pole or a person standing makes a right angle with the ground. So we're looking at a right triangle here. What's y going to be?
It's going to be the unknown. It's going to be the
Let's go through some of these. There's not much more important in math than being able to solve Pythagorean triangles easily. There's a couple of situations. There's this situation where you know the two short sides. What's this equal to?
WA. Oh.
Well, here's the equation. That's C. C squared equals A squared plus B squared. That is the Pythagorean theorem, probably the most important theorem in all of geometry, which makes C equal to the square root of A squared plus B squared. So what would C be here?
Four.
The square root of 3 squared plus 4 squared. So do each of those separately. Add them together. What do you get? Square root of 9 plus 16. What do those add to?
Those equal 25.
What's the square root of 25?
5.
That's the famous 3, 4, 5 right triangle. Okay? Now, we didn't have to do it the hard way. If you recognized a 3, 4, 5 right triangle, when you saw the 3 and the 4, you'd know that was 5 instantly. But it proves a point on how you come up with C. Okay? Now, there's only one other situation. And that's where you have the hypotenuse and one of the short sides. Well, if I solve this equation, and I'm going to call this A, this B, and this C. If I solve this equation for A, I get A squared equals C squared minus B squared, or A equals the square root of C squared minus B squared. That's the only other situation you have, is where you know the hypotenuse and you know one of the short sides. And so to solve for the other short side, use this. Start with, all of them start out with square root of. So if you're solving a right triangle, you want your answer to start out square root of, just like when you're solving an equation where you take the square roots, you want your answer to start out plus or minus. Well, all of these are square roots of. So when I'm solving for the short side, it would be the square root of 5 squared minus 4 squared, which gives you the square root of 9, or 3. And those are the only two you have to memorize. So let's memorize it. If you're solving for the hypotenuse, it's that. If you're solving for one of the short sides, it's that. If you were solving for the other short side, it's basically the same. You start out with the hypotenuse squared minus the square of the other short side. Okay? So, in actuality, there's really 3 situations, but 2 of them are almost identical. 2 of them is where you're solving for the short side. Okay? Now, this problem that they just gave you kind of tries to trick you. What would this side be, according to our formulas here? We're solving for a short side, right?
Yeah.
So what is it? What goes inside the radical?
Would be that'd be 12 squared.
Minus.
Minus 5 squared.
There you go. It's always, everything's always squared here when you're solving right triangles. Okay, well, in this case, that's the 144 minus 25. What is that? That looks like
119.
119. Can I simplify that? The answer to that is it would have to be divisible by some perfect square number. Okay, starting at 2 squared. In other words, we ignore 1, but is it divisible by any of these numbers? And I don't have to go much bigger than that, because once I get there, I'm beyond half. Is
I'm not sure.
119 divisible by any of those? The answer is no. First of all, if a number is divisible by 9, its digits have to add to 9. Well, these digits add to 1, 11. Okay? It's not divisible by 16, it's not even. It's not divisible by 25, those go 25, 50, 75, 100, 125. It's not divisible by that, or that, and it can't be divisible by anything bigger than 64 because 64 is more than half of that. Therefore, that's simplified. That's your answer for how far the ladder is from the wall. Square root of 119. Now, the reason I said they try to trick you is because they want you to memorize the two perfect Pythagorean triangles. 3, 4, 5, and what's the next one? 5, 12, 13. Those are the two smallest that you can possibly have that are all perfect integers. And they show up so often on tests that it's well worth your time memorizing it. It saves you from having to work through the math of the Pythagorean theorem. In other words, if I give you a triangle and I say, this is 6, this is 8, well, if you know the 3, 4, 5 triangle, it's not just 3, 4, 5, but it's any multiple of 3, 4, 5. So that would have to be 10. And I don't have to do the math. Or if I gave you 5, 12, you'd know that was 13. Now, here's what they gave you was 5, 12. That's not 13 because the 13 has to be the hypotenuse. But it would be very easy to make that mistake. If you were familiar with the 5, 12, 13 triangle, you might look at this and say, well, this has to be 13. But remember, the hypotenuse always has to be the longest side. So whenever you see a ladder problem, it's just a triangle problem. Always. A right triangle problem, I might add.
Hi, yeah. Did you have a nice time?
Yeah.
Great. Well, we're talking to David. Okay, so we're on 19.
When you are solving radical equations, the goal is to isolate the radical. Once we isolate the radical, we're going to square both sides and solve it. So what's my first step? What's the next line?
We could add 8.
Okay, so what's the next line?
4 square root x plus 2 equals 24.
Next step, next line.
You could divide by 4.
Okay.
So it would be x square root x plus 2. Equals
24 divided by 4.
yeah, 6.
Okay. And next step, next line.
You could square root everything.
Square everything.
Square everything.
Remember, there's a difference between square root and square. They're inverse of one another. But in this case, I want to square everything to get rid of that radical sign. So that's what I'm going to do. And what's the next line?
X plus 2 equals 2.
What's 6 squared? 6 times 6.
3.
36.
Oh, 36.
Notice there's no plus or minus needed here. We're not square rooting both sides of the equation. We're squaring. when you square everything, not only is there not a plus and minus, but if there was a minus, it becomes plus. In other words, it's always plus. And the final step?
Minus 2.
So there's your solution. Now, there are certain types of equations where you can get extraneous solutions. One of them is when there's radical signs, the other is when there's absolute value signs, and the third are when there's logs. I don't know if you've had logs or not, I don't think so. But we do have radical sign in this one, which means that it's worth checking the answer. Sometimes if you get two solutions, almost always one of them is no good. You have to throw it out. So let's just see if this works. 4 times 34 plus 2 minus 8, is that equal to 16? Well, what's that?
36.
Square root of 36 is 6. 4 times 6 is 24. Minus 8 is indeed equal to 16. Checks out. Okay. Cube root problems are exactly the same. We're going to isolate that, and then we're going to cube both sides instead of squaring both sides. In other words, our goal is to isolate that and then get rid of the radical sign. So, first step?
You could minus 2, which would be cube root x equals minus 3.
Good.
Then you'd cube both sides.
Okay, next line.
You'd have x equals
minus 3 times minus 3 times minus 3.
negative 27.
Good.
Oh, positive.
No, you were correct first time.
Oh, yeah.
In other words, minus times minus becomes plus. So now it's plus 9 times minus 3. You know, in other words, when I multiply those two together, I get this. Now a plus times a minus is a minus. So it's minus 27. And if we plug that in, the cube root of minus 27 we know to be minus 3 plus 2 equals minus 1. That also works. Okay. This one here, what's our first step?
Hey, David, hold on for a second, would you? It was x minus, what was it?
X equals negative 27.
All right, thanks.
Okay. What's our first step going to be?
You could subtract 5.
No, it's inside a radical sign. We can't do that. In other words, if I had something like this, I can't subtract 5 from both sides of that equation. I got to get rid of the radical signs before I can do any manipulation with the stuff inside it. How do we get rid of the radical signs?
Divide.
How do we get rid of the radical sign on the last two problems?
I mean, you root it.
Square it.
Get those straightened out.
You're getting somewhat confused between root x and x squared. Over here I'm squaring it. Over here I'm rooting it. If I want to get rid of the radical sign, I have to do the opposite of what's being done, just like every other algebraic process. In other words, if I'm subtracting something, I need to add it. If I'm dividing by something, I need to multiply it. Well, what's being done to this quantity is it's being rooted right now. So to get rid of that rooting, I got to square it. What do I get on the left and the right?
X plus 5 equals 3x plus 7.
Next line.
Well, you could subtract 5 now because it's out of the thing. So x equals 3x.
Do both of them at once. Do both of them at once and leave the x on one side of the equation and the number on the other.
So you'd have 2 equals 2x.
Almost. Let's do them separately. So your first step was to take off the 5, right?
Yeah.
So that gives me this. 7 minus 5 is 2. Now combine the x terms. And if I want them on the left side of the equation, which I asked for, then you got to move this 3x over to here.
So you'd subtract 3x.
So what's 1x minus 3x?
Minus 2x.
Okay, so I get minus 2x there. I still have this 2. And now what's the final step?
Divide
by
2. So.
No. Divide by negative 2. This is the whole coefficient. We got to get rid of all of it. If I divide just by 2, I'm going to be left with negative x equals something. If I want to isolate the entire just x, then I got to divide by negative 2. So what's the answer? X equal?
X equals negative 2.
Negative 1.
Or negative, oh yeah, negative.
Don't forget, you divide on each side.
All right, now let's check that. If I plug it in, I get the square root of 4 equals the square root of 4. Oops, excuse me. At some point, you'll get radical equations where you get 2 solutions and one of them is no good. And you only discover it by plugging it in. None of these, though. How do you get the mean? Well, first of all, let's create a stem and leaf plot. Stem and leaf plots are about as easy as it gets. You take the decimal point and you turn it into a vertical line. So, or not quite that. I'm sorry, that wasn't quite correct to say. There's the way I represent 18. There's the way I represent, there's also a 19. There's 2 19s. Now let's look at the 20s. There's, in other words, to the left of the vertical line is the tens digit. To the right of the vertical line is all of the single digits. Well, tell me what I should write here. There's a 20 for sure. What else?
22. No, 21.
Let's put them in order.
21.
21.
So there's 1 21. How many 22s are there?
3.
So there's 2, 2, 2. What's next? Is there any 23s?
No.
How many 24s?
There's 3.
What other 20s are there?
25.
Okay.
There's 2 of those.
There's how many?
2.
Okay. I think that's all the 20s. The next thing is the 30s.
Which is just 1.
Okay. And I wouldn't do so, but I noticed in the book that you could put a 4 in there with no number. If there's nothing following that, then it means there's no 40s. Okay? Just for your info. It doesn't really apply here. You don't need to put it in. But say there were some 50s. Well, if there were some 50s, I might put that 4 in just to fill in the gap. I'd put a 4 with nothing there, and then I would put however many 50s there were below that. Let's talk about the definition between mean, median, and mode. Mean is the arithmetic mean. That's what they're talking about. Same thing as average. How do I get the average?
Well, you add them all up, then you divide by how many numbers there are.
Okay. You got a calculator handy?
Yeah, you use this old one. Use that one. Well, that works.
It's better to add them up from this list here, I think, rather than the stem leaf. But so add all those up. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's extremely easy to make a mistake when you're doing this. I had a student the other day, both of us were doing it, and we both made 2 mistakes. In other words, when you're looking at a list of numbers, and I said, how many 22s are there? You can't believe how easy it is to get it wrong. So when I'm done, I count up how many I have and make sure it's the same as I have down here. And that way, at least I know I have the right number in each. If they're not the same number, then I missed one. What do you get when you add everything up?
292.
Divide that by 14.
20.
That's not 20. 20 would be 280 divided by 14. So it must be 20 and 12 fourteenths, 20 and 6 sevenths.
Yeah, the calculator, I think, came out, David, 20.908.
Hold on. 292 divided by 14. I get 20.857. They don't ask, or they don't tell you how they want it rounded off. So,
No.
actually, the way I wrote it there is the most accurate.
Okay. Which one, 20.7?
20 and 6 sevenths. In other words, that's a rational number. A rational number is where I can write it as a fraction, and it's perfectly exact. If I write that number as 20.857, that's rounded off. I dropped a 142 that followed that. And in fact, it goes on it repeats many times. So this concept of writing a number precisely comes up when you're dealing with fractions and decimals also. All right, that's mean. That's pretty easy. Average, add them all up, divide by how many. Median is what?
It's the middle number of the entire set.
Okay, now the stem and leaf plot comes in handy. We have 14 numbers. What's the middle number? Which one?
It's going to be the 7th number.
No. If there's an odd number, then it's just 1. If there were 15 numbers, it would be the 8th number. If there were 13 numbers, it would be the 7th number. But there's 14 numbers. So it's halfway between the 7th and the 8th.
So wouldn't you add both the 17th and the 8th and then divide by 10?
Yeah, there's the 7th number, right? 1, 2, 3, 4, 5, 6, 7. There's the 8th number. What's halfway between there? 2.
Yeah.
What if this were the 2 numbers? What would the median be?
3?
Yes. In other words, when I say halfway between, I mean you add the two numbers and divide by 2. But if you have the same two numbers, then it's just that number. You still add the two numbers and divide by 2. There's 2 plus 2 is 4, divided by 2 is 2. What does mode mean?
What number appears the most?
Which one is that?
Would it be 22?
Also 24. So there's two modes. There's 22 and 24. Notice there's 3 2s, there's 3 4s. So the mode is not always just one. And if there's none, in other words, let's say nothing was repeated, then the mode is none. Or I suppose you could say all, but I've seen it in a statistics book where it says none. In this case, there's 2 that are the mode, 22 and 24. So you would list both. All right, it's 3 o'clock. Why don't we stop for today? And how much of this statistics stuff have you had in class?
We just started, so only a real tiny bit.
Okay. All right. I'm not a great statistics expert. It's the one subject I do not tutor. I know enough to know mean, median, and mode, and I know lower and upper quartile, and I know box and whisker plot, and I know interquartile range. I think I could even figure out central tendency, but I don't know what residual is, and I looked it up in my books, and it doesn't have it. I'll see if I can figure it out by Wednesday, but that's something you may want to do a little bit of research on your own.
They're pretty easy for me.
He'll take a stab at it, David.
Okay, if you have a book that gives these definitions, just go over them. I know everything here except residual. I think I even know central tendency, although you might want to look that up also. And then what we can do on Wednesday, if you like, is review these last couple of statistics things, and then just go back and I'll make up problems and test you on similar problems that are on these 2 pages.
Yeah, that's what I was thinking we should do, so I can have it fresh in my mind.
Good.
Without any bumps.
Hey, David,
Yeah.
do you have like 1 or 2 minutes that I could just ask you a quick question?
Sure.
You know, if you take the picture of the questions that he sent you, you know, I just wanted to run through this quickly. I wanted to sort of get an idea to make sure that we knew what field each question was looking at. So just hypothetically, if you looked at question number 1, that basically is a polynomial problem, isn't it? I mean, it's a reduction, a simplification.
Well, I'm not sure I know all the terminology. This is a radical simplification, is what I would call it.
And what about the next one? Solve the equation. That's
a quadratic.
Quadratic equation. Then the next one is charting a quadratic equation.
Right.
Then 4 is factoring.
Quadratics. This is factoring quadratic expressions.
Quadratic expressions. And 5 would be that perfect square trinomial subset of questions or whatever.
It means take a quadratic and see if it breaks up into a linear factor squared.
Okay, and then I guess we get another quadratic equation.
Yeah,
is 6.
quadratics are big, so is 7.
6, 7, 7. Actually, 8 is graphing them.
8's a quadratic, that's a parabola.
9 is same thing, it's graphing. Then these are simplifications.
9 is also a quadratic parabola. All quadratics are parabolas.
Once you go through
that's all exponents.
And what about 10 then? Is exponents?
Exponents.
Okay, and then what about 11?
11 is fractional exponents.
Okay, exponents, fractional exponents. All right, what about 13? Excuse me, 12.
12 is fractional exponents also. the rules of exponents.
13.
So how you turn a radical expression into a fractional exponent.
Yeah, that rational one. Then you got, again, graphing a function. So we got 14.
That's the square root function.
Yep, same thing on the back, 15. Then let's see, what about 16? These are polynomials.
Well,
Is that? No, actually,
15 is a cube root expression.
Okay. All
16
right.
is simplifying radicals.
Okay.
18 is Pythagorean Theorem.
Mm-hmm.
19 is solving radical equations.
Okay.
And 20 and 21 are statistics.
No statistics. All right, I just want to make sure that we made sure on the sheet he went in, he had all the headings. All right, David, well, unless I schedule you another one, I guess we're going to see you then on Wednesday. And I know it's in the calendar. We'll see you then. I don't know.
Wednesday at 5.
Wednesday at 5. Appreciate your help, David.
You're welcome. Have a good one.
You did a good job. Fresh.